Hey everyone, today we're going to look at the equation of a line in R3 or a 3 space. We're going to extend some of the things we've done with lines in R2, just take them to add a third dimension. So let's get started. We've previously discussed lines in R2, and we looked at various forms for an equational line in R2. So today we're going to look at R3 and various forms of equations for a line in R3. So here we have an example. This time it's just for 2 points in 3 dimensions. But the things we did in 2 dimensions kind of still apply. You know, it doesn't matter that we're in 3D. If you want to find a vector that goes from A to B, you know, a vector that tells you the direction from A to B, like how far in the X and Y direction to go, X direction to go, in the Y direction and Z direction. Well, we would just find the vector AB, just like we did yesterday, just here there's a third dimension. So a possible direction vector for this line would be AB, and we would get that by taking the position vector for B and subtract from A. And that looks like -1 plus 2 is 1, -3, -7, and 4. So finding a direction vector for 2 points in R3, it's as easy as we did with R2. Just like in R2, so if we have a point on a line and a direction vector, then we have enough to state the equational line. So if you think about it in 3D, a line going through 3 space, nothing really changes from R2 in the fact, like in terms of to describe a line, all you need is a point on that line and to tell me which direction to go. So it's the exact same thing with R2. It's just this time our points will be in R3 and our direction vectors will be in R3 as well. So we're just going to do a natural extension of our vector equation of a line in our in parametric equations of a line, just add a third dimension. So the vector equation is R equals R naught plus T times M, where T is a real number. You'll notice this is the exact same definition as R2. It's just this time our R naught is our initial point. X naught, Y naught now has a Z component as well. And our direction vector now has more than 2 components. It has a third component. And if we take the vector equation and break it up into components, well, X will be X naught plus T times M1. And we'll do the same thing for the Y's and Z's. Y naught plus T M2, and Z equals Z naught plus T times M3. And we now have a natural extension to the equational line in R3. So just as a little visual here, you can copy this down on your page if you have room there. So just consider, I'm just drawing any 2 points in R2. If I wanted the equational line, through A and B, what I need to get to that line. So a position vector that gets me from 0, 0 to that line. And then I need a direction vector, and in this case, AB. So a little visual to see what's going on. It's much the same as R2. A position vector to get you to the line, a direction vector to tell you where to go. So the above example we had, we got that M, we've already calculated M by finding the vector AB, that possible direction vector, and we got 1, -7, 4. Of course, BA would work, -1, 7, -4. Any scalar multiple of this would work. The vector equation of our line and a possible vector equation. So possible vector equation, I'll pick point A. So point A was negative 2, 4, 3. I could have picked B, but I'll just pick A. Plus some scalar t times our direction vector, 1, negative 7, 4. And where t can be any real number. So that is a vector equation over line. Using this vector equation, the parametric equations will look like this. Negative 2 plus 1t. Y is 4 minus 7t. Z, 3 plus 4t. And we have the vector and parametric equations for our line. So as you can see, it's very similar to R2. It's a natural extension. Why don't you try it? Here's a line, a different line, going through those 2 points. Can you find a vector equation and then parametric equations? If you want to pause the video and try that, and unpause when you're ready, or you can follow along with me. So for a vector equation, we need a direction vector. AB is always a good choice, but you could do BA. So 3, 6, negative 4, less 2, negative 1, 5. So a good direction vector would be, that's 1. 6 subtract negative 1 is 7. And then negative 9, I believe. Yep. And so here we go. Just to be different, I'm going to choose B this time. So 3, 6, negative 4, plus some scalar t times our direction vector 1, 7, negative 9. So my guess is that likely you at home probably chose A, and you have 2, minus 1, 5. And you're not wrong. You're right, and I'm right. And because if you use a different starting vector than I did, you will have different parametric equations than I did. But again, that's okay too. So x is 3 plus t, y is 6 plus 7t, z, that's an awful z, z equals negative 4 minus 9t. It's that easy. We can do it. We did an example last lesson of determining if a point is on a line. So we can do the same thing with lines in R3. So I'm going to check I'm going to use my parametric equations. So you can use yours. We should get the same conclusion either way. So I'm just going to rewrite my parametric equations. So x is 3 plus t, just so I don't have to keep flipping back and forth. Y is 6 plus 7t. Z is minus 4. 9t. Okay. So to start off, I'm going to see what x value, or what value for t gives me an x value of 0, right? And that's an easy one to solve. T equals minus 3. Now I'm going to give you an alternative to the solution we did last day. If that point is on the line, I need t to be minus 3 in order to get the x value of 0. What does that t value of negative 3 give me for y and z? If 0 minus 15 is on the line, I should get minus 15 for y and 9 for z. So I'm going to sub in for y and z, and this is how I'll check this one. So yesterday we solved each of these equations and we see if we get the same value for t. This is the same idea, it's just a different way of going at it. Y is 6 plus 7 times negative 3. 6 minus 21 is negative 15. That's good. Z is negative 4 minus 9 times negative 3. And negative 4 plus 27 is 23. And that's not good. So it worked for Y, but it doesn't work for Z. So 0 minus 15, 23 is on the line. But not our guy. No, the answer is no. The next thing we need to talk about is we talked about normals of lines in R2. Any normal to a line in R2 was going to be parallel, right? If I had some line I have some normal to that line. That's one possible normal. Another possible normal might go down here, but it has to be, that's N1, I'll call it N2. They have to be parallel. That's not the case with lines in R3, because in R3 you have this one extra dimension. And so if you can imagine, like take your pencil or pen, that's a line in R3. I can take a second pen, and this is a possible normal, but I can rotate my pen around, right? Moving out of the camera. And as I rotate my pen, all of these are possible normals, but none of them are pointing in the same direction. I think the diagram here does a good job of that. So in R3, you can have normals to lines, but they're not necessarily parallel to one another. All right, that's actually it for today's lesson. We took what we did in R2 and extended it to R3. I just felt like it was too much to do in one day. One last thing to share with you is we've seen lines in R3 have a vector equation and parametric equations. Lines in R3 have no y equals mx plus b form. And the answer to that y is really simple. B in this case is the y-intercept, and a line in R3 does not necessarily have to intersect any of the axes anymore. Also, M, you guys defined in your grade 9 courses, rise for run. In this case, that's fine for 2-dimensional lines, but in 3-dimensional lines, we've got rise and run and some other direction as well. So it's impossible to state a line like this way. And because there's no unique direction for the normal, there's no unique value for A and B. And even in R2, even though you can have different normals, the fact that they were parallel, it always gave you the same Cartesian equation if you reduced it down. But because A and B don't have to necessarily be scalar multiples, lines in R3 don't have y equals mx plus b form. They don't have standard form. We have our vector equations and we have parametric, and that's all we can do for lines in R3. So hope you enjoyed that lesson. Here's some practice from the same set of practice as our last day. It's just these problems focus on lines in R3. In our next lesson, I'm looking forward to it. We're going to talk about the equation of a plane in R3, so it should be fun. Hope you guys stay well. We'll see you soon.